So we're going to be doing a couple of things in this lecture. Specifically, we're kind of covering two very different topics. We're continuing discussing some of kind of the underlying foundations to all statistics, some of the things we need to keep in mind no matter what statistical analysis we're doing, and no matter how simple or complex that analysis is. But at the same time, we're also going to start looking at overall, what are we covering this semester and what makes it different from last semester. So kind of picking up on the review of what we've dealt before, I think it's important to just take a brief moment to go to one of the most simple statistical equations that we covered last semester, and that's the z-score. And again, that is simply anyone's individual score minus the mean of the total data set divided by the standard deviation. And the reason that z-scores are important to keep track of is, one, they're a handy little tool if you're needing to compare people's relative positions in a normal distribution across different types of data, different samples, etc. So for example, if you're simply wanting to know, based on one set of measures, someone was in the bottom 30%, would they be similar to someone that you had different data from a different data set on, as far as, again, their relative position relative to the rest of the data that they had. So basically, this is a good technique for doing quick and simple comparisons of individuals across different data sets or different sources of data that doesn't ask the question, how did they score in each test, but ask the question, how did they score relative to everyone else taking that test? Now, this still may not provide a perfect comparison, but a lot of the times it does give us more information than if we were trying to compare, for example, someone's score on a test that scored from 2 to 38 compared to another person's score on a test that was scored from 0 to 100. Those two means, or those two scores of those two individuals, might not actually really give us much information. But if we had their z-scores, we can start to get an idea. The other thing about the z-score is it's a good reminder of the fact that most statistical analysis, especially if we're talking about mean scores and standard deviation, are based on the assumption of a normal distribution. And that's because if there is a normal distribution, the z-scores and the mean scores start to have meaning. In other words, the mean has meaning because we know that with a normal distribution, about 50% of the people are below the mean and about 50% of people above the mean. And if that's true, we can then use these scores to get an idea of people's relative position. How many standard deviation units are they above or below the mean? And again, a quick reminder that with z-scores, if your z-score is 0, that means you are dead center of that distribution. Half the people scored higher than you, half the people scored lower than you. If you have a negative z-score, it means you are below the mean. And again, whatever your z-score is, for example, negative 1.0, that means that you are one full standard deviation unit below the mean. Likewise, if your z-score is a positive value, that's how much higher in standard deviation units you were above the mean. And again, assuming a normal distribution, that also gives us some information. So for example, if someone has a z-score of 3 on a test, we know they scored higher than 99.7% of everyone that took that test. And likewise, if someone actually had a z-score of negative 3, we'd know that they were lower than 99.7% of the people that took that test. So just remember that z-scores are a handy tool. They're one of the simplest statistics, but also our interpretation of data, our interpretation of individuals and of mean scores, no matter how advanced the statistics, are still kind of centered around this idea of normal distributions and the assumptions we can make about a normal distribution. So again, just broadly remembering that all inferential statistics, from the simplest t-test or correlation to the most advanced analysis we're going to cover in this class, at the end of the day, theoretically, it's just the variance of the effect, mean differences or covariation on the top of the equation, and all other variance on the bottom of the equation. So again, just theoretically, what we're looking for is there more effect or systematic changes than there is just random noise? If there is, that's usually when we can claim statistical significance. Now, we're also going to be talking about the advanced statistics that we're going to be covering this semester. And what we're going to be looking at is primarily multivariate statistics. Now again, the name of this class and the focus on multivariate statistics might seem a little overwhelming, but the simple fact of the matter is, for the vast majority of analyses that we're going to cover this semester, we are simply adding another layer to what we've already covered. So when we were looking at factorial ANOVAs, we had main effects, We had interactions, and we had simple main effects, and we had post hoc tests, all of which we had to do. With multiple regression, we had to actually look at each individual predictor. We had to decide if we were using covariates or blocks, and we also had to look at the analysis based on possible interactions and even dummy codes. When we add multivariate statistics, all that we're doing by multivariate is adding additional DVs. So we'll have to run through that same process for each dependent variable if that omnibus test says we have statistical significance. We're also going to be talking about some other advanced statistics in this class, mainly kind of focusing on very specific problems that don't fall into the realm of what would normally be handled by our big kind of package of statistics. And our big package, by the way, is the ANOVA and MANOVA, or the multiple regression or regression. Most statistical tests will fall into one of those two broad categories. And in fact, most statistical technique classes will focus primarily on those tools. However, there are some specific situations, especially if we start looking at changing what the DV is, which might require us to use statistics outside of those two packages. We're going to continue kind of focusing on how do you select which statistic to use and reviewing those basics. And a part of that review of the basics is, again, no matter how complex the analysis, we still need to assess the distributions, and we still need to make sure that we're checking for our assumptions. So again, we already have dealt with multiple regression in our first semester together. We are going to continue looking at multiple regression and ask even further, what can we do with it, and what are the positives and negatives of using multiple regression? We are definitely going to spend some time on multivariate analysis, where there is more than one DV, and most of that time is going to be spent looking at the MANOVA, where we're actually using categorical predictors on multiple continuous DVs or outcomes. We're also going to be spending some time on kind of non-standardized or not as easily categorized tests, including non-parametric tests. So we're going to look at some tests that are very specific in what they were designed to do and when we'd use them. But we're also going to be looking at non-parametric tests, and a non-parametric test is simply meaning the DV is no longer continuous, it actually is categorical. So hopefully we'll be getting all of those into our toolbox this semester. And again, I want to really stress, the goal is not to become a master of every one of these techniques. The goal is to understand the technique enough to where it makes more sense when you read it in a research article. You're a better consumer of those kind of statistical techniques, and you have enough knowledge and at least a little bit of experience using it that if you were looking at SPSS or being required to run one of these techniques in your career as either an academic or a practitioner, you would at least know where to look to make sure that you're understanding what you're wanting to do. You'd have slides to go over, you'd have review materials, you'd be able to figure it out. That's really the goal of these two classes. So we're not trying to make it a toolkit there, every tool you know exactly how to use. It's more of, honestly, we're trying to make you familiar with the tools in that toolbox to where you at least know which tool to pull out. And then once you've pulled it out, you'll know where to look for the instructions to make sure you're using it correctly. So we're going to talk a little bit about what are multivariate statistics. So multivariate statistics include more than one dependent variable in the overall omnibus analysis. And probably the most common multivariate statistic is the multivariate analysis of variance, the MANOVA and MANCOVA. So basically in this situation, the multiple analysis of variance, if you have any kind of model where you have multiple outcomes, multiple DVs and they're continuous, and your independent variables, your IVs, are categorical in some form, that would be MANOVA. If you also want some of your independent variables to not actually be treated as an effect or something you're interested in, but you want to basically remove them from the analysis, that would be covariates and the MANCOVA. And again, when we look at MANOVA and MANCOVA versus ANOVA and ANCOVA, really the only difference here is adding quote-unquote layers to the onion. We're going to talk a little bit about canonical correlation and regression, and that is correlation and regression used in a non-parametric fashion. In other words, we only have one DV, but that DV is no longer continuous. We're going to look at principal, component, and factor analysis in more detail, and this really kind of leaves the realm of IVs and DVs, because with principal, component, or factor analysis, we're not necessarily asking if one set of predictor variables predict outcome variables. What we're actually asking is, we don't have an outcome variable. We're looking for structure within a broader set of data. So factor analysis probably most famously was used to actually identify the big five personality concepts, looking across hundreds, if not thousands, of individual predictors of personality. What they found using factor analysis was that no matter what scales you were using, they tended to clump into five constructs. And from that data, they were able to extract kind of the big five model. So factor analysis is usually used more in examining a series of questions looking for underlying constructs. But because of that focus, we're actually focused on every variable. We're kind of looking at no IVs and all DVs. We are going to talk about structural equation modeling. We're not going to get too in detail with this, as if we actually were trying to learn how to do a structural equation model, one, you need specialized programs to do it, and two, it actually is probably a class unto itself. However, structural equation models do show up enough in the research in all fields that it's probably at least a good idea to get an understanding of what they work as. And again, generally speaking, when we look at a structural equation model, we're starting to get away from the lands of IVs and DVs and are kind of getting more towards a series of factor analyses, in other words, looking for underlying constructs in a series of questions, but also then looking at the interrelationship between those constructs. So we're no longer looking at necessarily three constructs predicting an outcome. We're looking at the interrelationship between multiple outcomes. We're also going to talk briefly about contingency tables or multi-wave frequency analysis. And this is kind of, best way to think about this would be, it's multiple regression if everything is categorical. So your outcomes and your predictors, all variables are categorical. It's kind of the way it was described to me in the very first class I ever took that covered multi-wave frequency analysis, is it's kind of like chi-square, if you're familiar with that statistical technique, on crack. And that is a direct quote from Dr. Korchmaros. And again, we're not going to get into the complexity of that, and it is a fairly complex technique, but we'll at least touch on it enough for you to understand if you run across it in analyses. Of course, we're going to continue detailed in multiple regression. We're going to look more at multiple regression to get better experience with it, as it is kind of the kitchen sink of statistical techniques. But we're also going to be looking at different ways we can use multiple regression. And there's a fair amount of subcategories of multiple regression that, again, we're not going to get into extreme detail on, but we're at least going to touch on. And those include time series analysis, so basically looking at how things are changing over time. Survival analysis, basically the time it takes someone to get to a certain event. We see that a lot in medical research, and a lot of times it's somewhat morbid. A lot of survival analysis is literally that. How long does it take someone to die? But the reality is that if we're looking at drugs that are meant to handle extremely dangerous cases of deadly diseases, a lot of times what we are more interested in is not necessarily does the person live forever, but does it add to their quality of life and the amount of time that they have. And that's where we can see survival analysis, which is again a kind of specialized multiple regression. We are going to at least touch on mixed effects modeling, and this is a way to use multiple regression to really start to mash it into something that's not designed to do. So like if we're looking at multiple types of variables that are very different, so for example, we might have ordinal variables, we may have categorical variables, we may have continuous variables, and we're wanting to do more than just clump them into hierarchical blocks. We'll look a little bit at hierarchical linear modeling. That's using multiple regression to kind of do the same thing as structural equation modeling. In other words, we're not just interested in the relationship between IVs and DVs. We're starting to be more interested in the overall model. And as a final part, we are actually going to look at how to do some of the categorical data analysis that's built on multiple regression. We're not going to get too much in Poisson regression or profile analysis, though we will touch on what those are, because those are rarely used in our fields, but we will definitely look at logistic and ordinal logistic regression, and that is using a regression equation, again, as a non-parametric test. Your outcome is either a dichotomous variable, in other words, you're using a bunch of predictors to try to determine whether someone possesses something or not, whether they're hireable or not, yes or no, whether they're diagnosed with something, yes or no. Or ordinal logistic regression, where again, it's a categorical variable that's ordinal. So it's categorical. There is a least and a most, but there's not necessarily that continuous requirement that we expect in multiple regression. We'll also look at discriminant analysis, which allows us to use trend analysis, if you will. So we're looking at trends to, again, predict the percentage chance that someone would be in a series of particular categories. And again, both logistic and ordinal logistic regression and discriminant analysis are often used to allow us to do what's called mechanical decision making, where we have a bunch of information and data on individuals, and we're trying to use past knowledge of similar individuals to predict or to discriminate what categories we're assigning people to. And again, at the end of the day, I want you to always be asking yourself, what statistic is it and when would I use it? And when we'd use a statistic depends on the data for both the independent variable and the dependent variable. So the first question you can ask on a very broad level is, are my DVs continuous or categorical, and are my IVs continuous or categorical? If my IVs are all categorical and my DV is continuous, that's t-tests, ANOVAs, and MANOVAs. If my DVs are continuous and my IVs are continuous, we're at correlation, multiple regression, and potentially structural equation modeling. If my IVs are categorical and my DVs are categorical, we're actually at chi-square. So if all your data is categorical, we're at chi-square or multi-wave frequency analysis, depending on the complexity of that model. And finally, if your independent variables are continuous and you're trying to predict a categorical DV, we're at logistic regression or ordinal regression. Now, beyond that, we also have to ask the number of independent variables and dependent variables, and that will also start to determine within each one of those broad boxes what specific technique we should use. And again, remember that many of these tests have different versions that we use if it's a between subjects or within subjects design.